All right, just a few announcements. Your assignment number 1 has not been released yet. I'm working on that. It should be released tomorrow the latest. So you will get enough time, according to the calendar, to complete your assignment. But we'll do some recursion today for sure. I just want to finish off some motivating example about data structure, but it shouldn't take too long. Again, my office hours, 3 to 4 p.m., Monday, Tuesday, Wednesday, Thursday. If they completely clash with the class schedule, I'm sorry, but please reach out to my just reach out to me by email saying that you want to speak to me whenever you got trouble for the course, then we'll make an appointment. But I'll keep these 4 hours just for now. And we're going to do some trial attendance today by iClicker. It doesn't really count, but just for everybody to know what the flow is going to be like. Single check only, all right, just for today. Well, I'll do that maybe about halfway through the course, so we can also take a few minutes break at the same time. All right, so let's now go back to the introduction lecture. I just have a few examples just to give you guys a little bit motivation about how useful data structure can be. And the first one over here, you're definitely going to learn about the solution to it by the end of the course. It's definitely something you're going to learn. The other ones will be something that will go beyond this course, but I just want to mention them anyway because they are so practical and so useful for real application. All right, so last time we actually spoke about this simple loop over here, right? Let me just do a very quick recap. So we have a problem of mega city, and we got 10 million residence records that we want to store in the database. And our problem is, given the social insurance number that's unique among all the citizens, we want to say based on the unique identifier, we want to look for that particular residence record. So let's say this is the entire database, a very, very long array. And then it has 10 million resident records being stored. Let's say we got enough memory. So memory is not an issue here. And then we said, in order to do such search, we need a for loop, which you guys know how to do it, even from the first year. But we kind of criticize on this solution over here to say, well, in the best case, if the residence you're looking for is pretty close to the beginning of the array, then you don't really need that many iterations to really find out that particular residence. However, in the worst case, let's say if the residence sits very, very close to the end of the array, well, simply there's no resident there that we're looking for, in which case you have to scan through the entire array using 10 million iterations. So 10 million is a big, big number. So what we'd like to improve is, well, we want to explore the possibility to see if it is possible to minimize the number of iterations we need in order to search for such, to actually solve such searching problem. Indeed, there is. So what I want to mention to you guys very briefly is something you will learn after the reading week, but towards the end of the course. Something that we'll learn is something called balanced binary search tree. I will just give you some very visual intuition. And I wouldn't go too much into detail, but there will be something that you want to pay attention to. Okay, so what we need is a solution. Solution for efficient searching. And what you will need is something called balanced binary search tree. And I did mention this term last time as well, but you keep hearing about this term from me, even before we formally introduce it. But I'll just mention that again. So balanced binary search tree. It will look something like this. So we have some record at the top, which we call the root. And that is binary because it got 2 branches always. So we got another 2 children. And then we got further down like this. And then we got further down like this. And no worry at all about how exactly such structure will work. You will get lots of exposure to it in your assignment number 3 and also the lecture after the reading week. But in general, the way we visualize a tree wouldn't be in such concrete sense. We want to think a little bit more abstractly. This is how we normally visualize a tree, thinking that this is the root. And somehow this is the bottom level of the tree. And I'll definitely give much more detail into it once we get to the tree lecture. Right? So this is more like the bottom level. All right, so I want to speak about what I really meant by balanced. Balanced simply means, let me show you something that's unbalanced. if I got a tree that's like this, and then I have certain nodes that will go something like this, and etc. This will be something that's unbalanced because, for example, if the resident record happened to be here, I only have to go from here to here to here, only 2 iterations. Versus if the record happened to be here, wow, much longer path for me to travel to. I got to go from here, 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 all the way to here, which can be asymptotically very large. So if you got a binary search tree, that's simply not enough. It has to be balanced. Balanced in the sense that the furthest distance you want to go from the root to any nodes in the tree will be bounded by a certain number. That's something we have to argue mathematically once we get to the lecture. All right, so that's something you want to know. And then you want to think about for every search we want to do, we're going to go somewhere all the way to, in the worst case, to the bottom. And if that's balanced, it's guaranteed. If you got n records in the tree, that's being stored in the tree, let's say n records. And here's a mathematical property which we'll try to prove as well when we get to the lecture. It's going to be log base 2 n. All right, so you may have heard about this before, good for you, but we're going to talk about it precisely. And for those of you who, I'm pretty sure you know what log is, right? For those of you who don't know, or forget about the details, we also need log to do asymptotic analysis starting from next Tuesday. It may not hurt to brush up a little bit about log over the weekend. All right, but I'll review with you anyway. All right, so this is some facts you can definitely know right away without even understanding it. That's okay, log 2n. So let's now go back to our original problem over here. All right, assuming that we are able to store the 10 million records into a balanced binary search tree. Balanced binary search tree. And it's guaranteed whenever we want to go from the root to the bottom, it's going to be bounded by log 2 and then 10 million. Right? I'm just applying the number over here. Any idea what this number might be? It's way smaller than 10 million. It's roughly about 23 point something, which means we only need within 24 iterations to find the residence that we are looking for, as opposed to 10 million. All right, so you can see how efficient it is. So this will be the kind of sound decision you have to make whenever you want to implement a database. If your database size is only 100 records, doesn't matter which one you're using. You can use an array with 100 iterations, that's fine. But if you got 10 million records for your application to search through, you better use a balanced binary search tree. All right, so that's something I want to talk about. That's the first motivating example, which I wouldn't say too much, but I promise you're going to learn a lot about the tree and also different mathematical properties. And eventually we'll get to searching as well. All right, so that's the first one. Okay. All right, the second problem I want to talk about as well, as I said, this will be something called flight routing. Basically, just about how usually the flight, when they want to go from, for example, from London to Toronto, how do they actually figure out exactly how to go from one place to another? Well, for an airline company, let's say you want to go from London to Toronto, you may not have a direct flight. You may have to go from Toronto, first of all, to Munich, and then from Munich to London, right? So there will be kind of like a routing you have to do. In order to solve this problem here behind the scene, you also need data structure. But the data structure you're going to need is something called graph, which is a more general data structure than trees. But we wouldn't cover graph in this course, unfortunately. So this is something to keep in mind. Whenever you have any kind of like a routing problem, then you will need like a graph data structure, which you'll learn a lot in 3101. Okay, just for your information. Another routing problem here, for those of you who drive, for Google Maps, for example, let's say I want to go from Birch Run Center, and now I want to go from here back to my home. In that case, I want to know exactly live traffic situation and which might be the best route in terms of the shortest, not the shortest distance, but also shortest traveling time. Maybe taking one route is going to take me 40 minutes. Taking another route is going to take me maybe 30 minutes, something like that. So this is just another kind of routing problem. You also need graph data structure behind the scene. All right, that's just another one. All right. Yeah, just keep these two routing problems in your mind. Maybe after you have completed your 3101, you can actually think to yourself, if I want to develop a simple app to really do some routing, maybe from one location on campus to another, how would I do it, right? Think about it. All right, the final one, which I personally like a lot, which is something about compilation, compiler, basically. So compiler, again, it's not something we're going to cover in this course, but in order to implement a compiler, which will basically transform from one thing into another, is a very general technology you can implement by yourself. I'll give you two examples about what a compiler can do. Now, one thing I want to point out right away. Usually, the data structure you will need to master before you can implement a compiler is only a tree, not a graph. That means at the end of the semester, once we complete the teaching, once we complete the learning about trees in general, you will be able to implement a compiler. That might be something you want to dive yourself into over the summer. That'll be a very nice extra project you can do on your own. But I'll give you some example here. All right. So what I want you guys to see is something like this. Okay, give me one moment. I'll show it to you. All right, this is not Java. Think about this as more like a programming language that's designed by some small company. They have so-called domain-specific language, which means it's not really the mainstream like a Java or Python. It's just something the company or a person developed by themselves, just a language. Okay? I'll walk you through very quickly, and then I'll tell you what a problem we can solve. Okay? And then I'll show you the process quickly. Let's say we're trying to run a loop. We just use a keyword called across. It's more like a for loop. We say we will have a for loop over here. We want to go from, okay, sorry, there's a typo here, beg your pardon. So this should be 1 over here, okay? We want to go from 1 to n, and the loop counter is called I. And then in the loop, this is something we are trying to do. All right, we want to read some input from the user, and then we want to store the input into D. And then we're going to update the value of A, which was declared maybe outside the loop. And then every time when we update A, this is the value we want to update that into. And as for the B and C, they are declared over here. And you can assume D is declared elsewhere. All right, so that's a program. All right. So this example here, I want to mention there is a very typical use for a very old school or conventional use of a compiler, which is for program optimization. For example, whenever, let's say when you guys took a 2031, 2032, the C course, you know that C itself directly is not executable. What you gotta do is every time you try to compile your C into some object code or machine code, there will be some optimization that's done to the, from the source code into the machine code to be executed. And this will be some example about optimization, which is to kind of make your program a little bit more efficient to be run. All right. And just by looking at this particular loop over here, do you see any kind of inefficiency? Yeah?
Well, we calculate 2 times B times C every time we iterate.
Yeah, that's pretty accurate. Basically, your classmate is actually very correct. This expression over here, so don't worry too much if you haven't noticed that yet, but usually there will be some pattern that has to be identified by the compiler. This expression here, 2 times B times C, we say that its value stays invariance, doesn't change between the iterations. So it stays invariance between iterations. However, since 2 times B times C are always the value is always going to be used, also it doesn't change between the iteration. So why would you have to compute it in iteration number 1? And you will calculate again from scratch in iteration number 2, in iteration number 3, etc. You're wasting some computing resources for keep calculating the same expression that really doesn't change its value. On the other hand, the D here is pretty fine because every time you're reading input from the user, they might give you a different value. So there's no way to optimize it. Also for A here, you got to keep it here because A value might change between iterations because you are putting that to the left-hand side of the assignment, right? So it would be nice if we can somehow maybe move this expression up or out of the loop, and then make it to be computed just once, and then reuse it. All right? So what we'll see is something like this. So we have something called optimization. So the dashed line here simply means conceptually, this will be the optimization we want to do. All right? So again, there is a typo here. There should be just one. All right? So what we do instead is we are going to introduce a new variable here outside the loop called temporary, temp. And then we're going to calculate this expression here just once. And then we are just going to use it over here. Right? You can see once this is calculated, you can simply just use it once, right, in the loop. So you don't need to recalculate it every time. So that's an example for optimization, right? How can this be done automatically in general? What I just did was like a manual exercise together with you. But whenever you talk about compiler, it's going to automate what you think should be done. All right? So here is where data structure can come handy. The way to do it, this will be the whole picture. All right? So the idea will be, because I know that I cannot go directly from here into here automatically. The way to do it is I need to somehow, it's called parsed. We're going to transform the program into a tree structure like this. And then we're going to do some manipulation on the tree, which you guys will do in assignment number 3 and 4. Do some manipulation on the tree and transform that into another tree that's going to represent the optimized program. And once we got a tree here, we're just going to look over every construct over here and print it out. And that will give us the final program. So in summary, rather than going from here directly to over here, we're just going to go for a slightly longer route. But the good thing is it's automated. We're going to go from here into here, and then do some transformation on the tree to another tree, and then go from here to here. We can still end up having the optimized program. Okay, so, and this part over here, and I know that for you guys who are in engineering program, you guys didn't take 2001, so you wouldn't know what parse really mean. That's okay. That's something you may want to maybe learn, maybe on your own, outside the degree. So this will be something has to do with a compiler, right? You're just going to somehow transform this guy here into here, all right? And the tree here, I'm not going to bother you too much, but you guys can try. I'll make the diagram available to you. You can try to see why this particular tree can somehow correspond to this particular program. Okay, it does correspond to it, all right? Yeah, I think that's enough detail. So that's something that's very doable by the compiler. But in order to implement a compiler, you will need to know how to do transformation from tree to tree. And you guys will get a chance to practice in the assignment number 3 and 4. All right? Okay, final one. Okay. And that's just another little bit more recent application about a compiler. Okay. So rather than just trying to optimize a program for machine execution, we can say we got two very useful languages. Let's say we got Java at one end, we got SQL, database language, on the other end. Somehow we want to translate maybe from Java classes into SQL tables, and from Java methods into SQL store procedure, so you can do some updates or operation for queries, etc. on the SQL database. So this is something people also tend to do a lot in the industry. And of course, it will be very useful if you know how to implement that yourself. Maybe one day you want to say, I want to translate from Java into Python, or another language to just another language. Okay, I want to show you something diagram here, similar idea. So on this end over here, this is like a Java-like language. So you got class, you got attributes over here, you got different types of attributes, right? And also you got some methods over here, right? Don't worry too much about the syntax, just get the idea. We got attributes, we got methods, we got classes. We cannot simply directly turn this OO structure into SQL database, but conceptually, that's what we want to have. You can see this completely different language over here from left to right. So this one here, we got table, and also we got, I don't have store procedure here, but we got tables, and also we got OID, for the primary key, etc. And the way to really do such automated translation would be similar process. we'll go from the source program over here, Java-like, and use a compiler to transform that into a tree, which I wouldn't include over here, but a tree, like what we saw earlier. Once we get to the tree, you guys can do some transformation, some manipulation on the tree to transform that into another tree. And this tree here is going to correspond to the syntax of the SQL language. And once you got that tree, you can put it back to the actual syntax for the SQL. So that's also something we can do. So rather than going from here to here, we're going to go from here to here, here to here, and here to here. All right, that's just another example. And of course, having the data structure of tree working behind the scene is just critical. Otherwise, there's no way it's going to work. All right. All right, guys, that's about the motivating example I want to show you. So mainly about the trees and graphs. But of course, there are many other data structures like stacks, queues, hash table, but we'll get them. We'll get there. I'll mention more motivating scenarios there. Any questions? All right, good. No problem. All right, so we are done with basically, last time we talked about syllabus, and we just finished about the introduction for the course, and let's now get to the real lecture, all right, which is about recursion. All right, so, and I would suggest we take another 15 minutes or so, maybe lecture, because once I get to the more advanced example about recursion there, I would like to go until the end of the class. That one, I think it does require our full attention, okay? Okay, recursion. And the way I'm going to run this lecture here is rather than spending maybe 3 classes just repeating what I said or what you already have already learned in 2030 about recursion, I think I'm going to do 2 things over here. So what I'm going to start with, 3 things, sorry, 3 things. Number 1, I'm going to point to you the references about catching up with the basics of recursion, which we may not spend time doing the lecture. So when you catch up with the basics, which you find a need, if you run into any trouble, understand the basics about recursion, reach out to me, right? You want to do that as soon as possible. Otherwise, you will struggle a lot about programming assignment number 1, okay? And the second thing I will do is I'll just mention about some general principle about solving problems recursively. And also, I need to review very quickly about a concept you learned called callback value in 2030. We're also going to need that very badly for recursion. That's second thing, okay? So these 2 things will hopefully take about 15 to 20 minutes, and then we'll take a short break. And number 3 will be, remember I reached out to you yesterday about some advanced problem there, right? But if you haven't got a chance to do that, that's okay. So we'll do it together. And then I'm going to do everything from scratch on Eclipse. And I'm going to show you the solution. But I think the most important thing for you guys to really understand is about the insight into using recursion this way. And also how to trace the program in an abstract way. That's going to help you a lot when you actually solve the problems for recursion, right? So that'll be the plan. Hopefully we can do the most of it today, but I may have to carry over a little bit next Tuesday. And after this one, we'll talk about big O, asymptotic analysis. All right, one thing at a time. All right, let me talk about beyond this lecture right away, right? It's just about recursion. What kind of extra practices can you do? So coding bat, which I forgot to mention last time in the course syllabus section. So these are the 2 sites there. Coding bat, they actually got problems about recursion. So I would say you should read recursion 1 is more at the 2030 level. They are pretty basic. So for those of you who still want to review some basic, practice some basic problem, go for recursion 1 first. But recursion 2 is going to be around the level we will expect you to do in this course. And the problem I'm going to go over with you today will be one of them in recursion 2. And even that, after we have solved the problem together, I'm going to suggest some variants to the problem to make it even more challenging for you to think about. Right? You just want to do more and more challenging problems to get used to recursion. So recursion is actually quite a challenging topic to really grasp. I absolutely agree. But you guys are smarter than I am. So maybe just 1 course would be enough. It took me about 3 courses to really get through recursion. For you guys, maybe just 1, just 2101. All right, coding bat. So you can explore that, but we're going to talk about different, at least 1 problem in class. But if you try the problems there, and then you want to show to me your work and want to get some insight, get some hints, just come by, right? We'll talk. All right, this one Don't do it this turn. You don't have the time to really do it. Just like that's why I say it's a long-term solution. So beyond this course, if you want to really master the recursion, so there are two things I would suggest, right? Two things. Number one, you want to learn a so-called functional programming language. And I did include one of the most popular functional programming language called Haskell. That would be the best way to really train yourself thinking recursively. All right? That would be something for you to think about. Not this semester, right? Another one, you want to learn how to develop a compiler. Once you get to the compiler, remember the tree I talked about, right? Tree transformation is always recursive. So you always got to think recursively. So these are the two things. If you ever want to master the recursion beyond the course level, really something you want to invest your time. All right? If you want to talk more about it during the semester, about these two bullet points, feel free. I'm also happy to talk. All right, so that's something for, to say right away. All right, so a little bit more relevant to what you should do right away. So for the basic recursion, so again, it's assumed you already learned it in 2030. So this will be like a checklist about how well you have already grasped the recursion from 2030. So what really makes a method recursive? If a method calls itself. Easy. And also, how do you trace recursion using a call stack? That's something also very basic. So the typical example we'll use to trace recursion using a call stack may be the factorial or maybe the Fibonacci number. So I'm going to include resources for you to take a look at. I got some very nice lecture explaining them, but we are not going to spend time in 2101. Okay, we're going to do something more advanced. Okay, but you definitely should know how to trace recursion using a call stack. But for advanced example like the one we're going to talk about today, you don't really want to use a call stack to trace. That'll be too low level. You'd rather use what I call a recursion tree to really trace it. That's something I want to spend enough time with you. So you really want to get that technique right away. All right, we'll see. If we cannot finish today, I'll definitely continue on Tuesday. Right, call stack, you should know. That's a basic. And how do you really define and use something called recursive helper method? In order for you to solve a problem recursively, normally you don't really have a single method to do the entire job. You may have to have several methods, and some of them are so-called recursive helper method. You'll see example today as well. But for the basics, you should also check out the background information. So these are some example points you want to look into. And then now I'm going to point out some references to you for those of you who don't feel comfortable about recursion, even the basics. So I got two links over here. You can just go through them. So this is like a pre-recorded lecture. Pretty good. You know, they really cover all the basics. You can go over them. That's from 421. Another one which I did last semester with my students. So that one there, I talk about some very interesting recursion example called Tower of Hanoi. You may want to look into it as well. Okay, just to catch up with the recursion. Right, for these two, I'm not going to bother you with that in class, but please really catch up with the basic. You will need them, right? Spend some time. You still have time. It's still early. Don't forget the very first time that we're going to test your knowledge about recursion will be programming test 1 after the reading week. So you still plenty of time to catch up. All right, so how should you study these resources? There is a slide over here which will contain all the contents you're supposed to know. Take a look at the slides first. If you think you completely lost in the slides, then you may want to follow the video lectures more thoroughly. But if you got most of the stuff in the slides, maybe only certain parts you want to watch that part of the lecture video, right? I'll let you decide. And there is a past lab in 2030 about recursion. I put the starter code over here and also the solution over here. You can also click on the link to go to them. All right. And then just ask questions whenever you have. And what we'll do is we're going to look at some advanced example, and then we're going to give you programming assignments pretty soon. All right? Hopefully tomorrow, most likely. One more thing, and then we'll talk about some basic principle. If you go to the lecture site, right, you will see that things have been updated. I'll make it a little bit larger over here. All right, you can see that I already posted the slides I'm showing today. And then the exercise, the advanced example that we're going to go over starting from today will be here, the split array example. That's the starter code. I'll show you how to import it, just in case you forgot the details. And so these are the two recommended study I just mentioned on the slides. And there is another extra tutorial session about just one more example for recursion. All right, you can maybe I think maybe 1 or 2 examples there. But if you want to see more example, that's where to go. And finally, just for call by value, I'll mention the call by value concept very quickly today. But just in case you want to see more details, you can also take a look. Call by value is very important, actually, for this course, in order for you to program recursion. All right, any question about just the references I'm giving to you? All right, don't think we are skipping, because these are stuff we think you should really know before coming to this class, but you still got the opportunity and time to catch up. All right, just reach out if you got a problem. Okay, good. So for this lecture, review the basics. I'll just basic principle very, very quickly. And also, we're going to look at a more advanced example together. All right, principle. So what does it really mean to really solve a problem recursively? Okay, and I'm going to go over the concept about base cases, recursive cases very quickly. And then I'm going to draw some very quick connection to mathematical induction, which you guys learned in the math course, right? Very similar. Okay, so let's now talk about principle. Right? So first of all, let's talk about mathematical induction. Mathematical induction. And you guys know there's a distinction between weak versus strong induction, right? Okay, assuming that you know. And recursion is a little bit like the strong version. Meaning that, let's say I want to prove some property P for some, maybe from 1 all the way to some infinity, or just, you know, a large number. I want to prove some property. So what do we do? How do we do that? You may have to try a few so-called base cases, P1, maybe P2. Try them first. Make sure they work. And then you can assume for as many as you like. So for example, you can try to assume, maybe I will assume maybe P of maybe K, maybe P of K plus 1. For example, you can assume as many as you like. Assume. And then after that, you will have to somehow show that, for example, ultimately, P of n will actually work, right? That's kind of the mathematical induction. Not exactly, but that's pretty much what you learn in the math course. They nicely correspond to how we're going to talk about solving problems recursively. In the sense that if you want, let me leave this alone just for now, and let me talk about how you can solve problems recursively first, and then I'll draw the connection. You will be given problems to solve, like an input. It could be an array of size 100 versus an empty array, right? Maybe input can be of various size. If the problem itself is so small, the solution can be obtained right away. You don't need any further or even recursion. So this will correspond to the base cases for mathematical induction. That's something you can show right away. You don't need any further arguments or analysis. So when there's a small problem, base case, solve it directly. And usually base case is the way to make sure your recursion will terminate. I can mention that quite quickly, right? Given a small problem, so you want to make the base case ensure termination. Because if you keep making recursive call without terminating, you will just run out of memory, stack overflow. So you have to reach base cases at some point. And the second case will be if the problem itself is way too big for you to solve right away. We are just going to somehow divide the original big problem here into smaller problem. So each sub-problem over here must be strictly smaller, strictly, cannot be equal to, must be strictly smaller than the original problem. And then we assume, or we simply make a call to get a solution for each one of them. So this part over here is similar to how we assume over here, similar. We assume, we don't need to think further, just assume that we can make a recursive call and get a result back accordingly, all right? So this part over here, let me just show to you. So this part over here, once for each subproblem, we simply got the corresponding solution is really corresponding to the assuming part for the strong induction. And finally, once we got the individual solution over here for the subproblems, we can somehow combine them into a solution that's going to work for the original problem. All right, so that one will pretty much correspond to this last step over here. It's a very simple pattern over here, and amazingly, it's a very powerful one. Every problem you're going to solve for recursion, ranging from factorial Fibonacci to what we're going to talk about today, like a split array, they follow just the same principle. Just keep that in mind. So I would suggest, since you guys are still, trying to improving your recursion technique, every time once you have solved a particular problem, or even when you're sketching a solution, think about for each stage, what should be the base cases, and what should be the way you can assume about subproblems, and how you can combine the solution together. Always remember, all right? Yeah, this diagram here is just to say if a method calls itself, then it's a recursive method, right? Nothing exciting. Right, I thought this might be worth mentioning about the solution strategy for recursion that you should really keep in mind. All right. All right, and then I want to talk about one more thing about basic, and then we'll take a very short break. Okay, one more. Just about the call stack. So this one here, I'm just including the slide for you guys to look over. So that's just about whenever you got different method call, how you can put some method call onto the stack and pull it out, etc. Right? So you can go over that. If you got any trouble understanding what a call stack is, you can go back to the background study. We are going to talk about the stack data structure, maybe maybe closer to the reading week, but we're going to see how to use a stack to solve other problems. But I think the call stack, you should really make sure you know. And the best exercise you guys can try, all right, is to look at this Fibonacci sequence example here, and then you will try to look at the recursive definition over here, Fibonacci sequence, and then you will try to trace, for example, how can I recursively get to the fourth number, for example, in the Fibonacci sequence. And there is a video showing you how to do that. All right, so that's something I also assume you guys know how to do, the basic. All right, call stack. So we're going to do the more useful stuff for this course about how you can use a recursion tree to trace. That's something I want to spend more time on in the class. But for call stack, it's definitely critical. All right. If you got any trouble understanding about the call stack, again, reach out. We should really talk about it. Okay. All right. I want to talk about one more thing, and then we'll take a short break. So in order to really run recursion on an array, we have to use the so-called call by value over here. All right. So call by value simply means whenever you're using an array as an input, but between different recursive call, you're not really trying to make separate copies of the same array. You're basically trying to say, I want to pass just the address of the array between the recursive methods. So I'm never trying to recreate the array by wasting the resources. That's basically what the call by value is going to mean. But I'm going to visualize to you very soon. So what we're going to see is, also in the advanced example, normally you will have to pass, usually maybe just single input array, pass its address, its reference to the recursive call. And also you have to pass another argument here. So these two should really go together. You got a reference to the array, a single array. There's never a separate array being created. And also you got to say, for the current recursive call, which location or which range of location in the array am I going to look at? Right? I'll visualize to you right away. Okay? Okay, let's take a look. All right. Let's say I have a recursive method called m. It is recursive because you can see somewhere I'm calling m itself. Right? It's recursive, first of all. Right? And then I'm having some input array a. And then I have some indices from and to. So you can think about these two integer parameters. Of course, when you solve different problems there, you don't necessarily have to specify from and to. In the example we're going to go over, just one will be enough. So from and to just a very general. Okay. So these two will specify the range of elements to consider in the input array A. All right. So that's why I said they should really go together. You need a call by value just for the array reference, and also you need some integers to help you to see where to look at the array. All right, so a very typical way to write it would be when from is larger than 2. For example, typically from should be, if, let's say, give you some quick example. Let's say if I got an array, let's say A here. If I got 0, 1, 2, and 3. All right, so let's say four indices from, and then I'm just going to put it here, right? So in terms of the from and to, for example, if I say from 0 to 3, that one there is basically telling I'm basically going to, I intend to cover the entire range of the array. On the other hand, if I got, for example, from maybe from 1 to 3, and that one there is going to consider a sub-range over here. So there is no need to create a slightly shorter array and copy over the contents. All you got to do is, I'm going to pass the reference of this array here, and then change the range I'm going to look at. That effectively is creating some sub-array without wasting the spaces. All right. So that's kind of the strategy we're going to adopt. The special case would be, for example, if the from is 1 and 2 is 0, right? Something like that. So you can see normally from should be less than or equal to. But when you got from is larger than 2, that simply means we have no elements to look at. It's like an empty range, basically. Right? So that's why this will be the base case normally. All right. So this 1 and 0 over here, so this will be empty range. Okay, empty range over here. And when from is exactly equal to 2, so that means, for example, from is 0, 2 is also 0. That means we're looking at just element here, right? Just one element, right? It can only be a base case. So these are just two example base cases, which are typical. Let's look at a recursive case over here, all right? When I'm trying to make a recursive call, I'm basically saying I'm passing A here, that's call by value. The A here is basically call by value. So let me just make it a little bit more visual here. Let me say it again. I want you to consider these two lines. This line here, and also this line here, right? These two lines. Let's see exactly how they work. So here we got A is basically pointing to some array over here. That's a single array we have. To begin with, we got from and to. So for example, from can be over here, and to can be here. That means in the beginning, we intend to look at the entire array. That's how we start with. But the range is too big for me to think about, right? So I'm going to create some sub-problem. What I'm going to do is I'm just going to make a recursive call, which is over here. And the recursive call is actually going to go from plus 1 to 2. So that means over here, if you think about this is the from, and this is the from plus 1, right? That's the index just next to it. And that one there is actually going to consider just this sub-range over here, right? So think about, okay, let me put it here, okay, just right here. So whenever we are when we are making a recursive call over here, we're considering just the same array, alias. And then we are saying that the range is going to be disregarding the first element, which we presumably we have already handled that. So we're going to look at the rest of the array instead in this particular recursive call. All right? Just remember this kind of pattern here. We're using call by value, and it's so important to get it right. All right, one more example, and that will take a short break. Let's take a look at the tracing of this. All right? Let's say we got an array of size 3. All right? So let's say we got A2, which is pointing to an array of size 3. 0, 1, and 2. And we got A, B, C. A, B, and C. And we are trying to make a call over here. So we got, first of all, we start by N, A2, and then 0. A2, the length minus 1 should be 2. Agree? Right? Because length is 3. So we start with this one here. That's how we start with. So in the beginning, we basically just got 0, 2. So it's going to cover everything over here in the beginning. And imagine that we are trying to trace this particular call. So we're going to look at the code over here. So we got from and to, right? So think about this is the from value, and this is the to value. So you can think about from is right now 0, and to is actually 2. You can see that that one there, from larger than 2, is not true. So we haven't reached the base case yet. So we're going to look at basically a recursive case. And that one there is going to make a further recursive call. What should we make? We are just going to have another call to n, and then notice that we are still passing A2, just the same reference, referring to the same array. And now, rather than 0, it's going to be 0 plus 1, which will be 1, and then 2. So this one effectively tells you we're going to go from 1 to 2, and we're looking at this one here. Okay, one more. So starting from this, we have to do another call like here. And for this call over here, let's go back to the same piece of code. And now from will be 1, and to will be 2. So 1 and 2, right? Just very quickly. So 1 and also 2. And you can see that one there is already reaching the base case. So we are good. So we can do something to do with the base case, right? So this one here is, sorry, not equal just yet. I beg your pardon. So with from equal to 2, it's not the case for 1 and 2. So we have to make a further recursive call over here. One more. And that one there is actually going to be calling n. And we've still got A2 over here. And what should be the value? So from plus 1. So 1 plus 1 will be 2. So we got 2 and 2 over here. So now you can see that 2 and 2 is going to cover just this last element over here. You can see the range of the indices are basically shrinking. Starting from 3 elements, the entire array, to 2 elements, and then to 1 element when you make a further recursive call. And finally, 2 and 2 over here will satisfy the constraint for base case, and we're done. So it does terminate. All right. So this is the final base case. This example here is a little bit abstract. It's not really concrete, but that's okay. I just want you to pay attention to about the callback value. We're just passing the reference. And then we're just going to keep changing the integer value over here as we try to move maybe along the way in the array to look at different elements. That's the key to pick up. All right, any question? Yes?
So in call by reference,
Call by value.
No, I know. But like in call, are they the same?
No, call by value is really just the copy of the value. Call by reference will be more about the address. But anyway, call by value.
Like in the when we call the recursive, when we have a recursive call, we still like pass the reference of the array.
Mm-hmm.
So how is that call by value?
Call by value, okay. So very quickly. All right, guys, our good question here. I'll mention the call by value very quickly, but that's something you also want to read a little bit more detail into background. Okay, let's say this. Let's say we have the example I can give would be, let's say this. So let's say I got class person. Okay, let's say we got integer, the h. Okay, just that. As simple as that. And then we got person constructor over here, integer age, and then just normal constructor over here, right? So let's say that's our, okay, right here. Okay. So let's say we have some piece of code over here. So let's say if I got person let's say Jim equals person, let's say 23, let's say. All right, so we're creating a person. And now you can see Jim is basically a reference for some memory location, like objects, right? It's of type person. And that one there has the age of 23. All right, that's what we got so far. So what we want to know is, when we try to pass Jim, the reference, to some other method, what's going to happen? Rather than passing or copying the whole object into that particular method as the arguments, we're only going to pass Jim itself. But let's see exactly how that can be done. Let me just define another class over here. Let's say we got utility. All right, so let's see here. So I may have something called, let's say, void. Let's say change the age of the person. And then I'm expecting some person over here. Let's say P. All right, and then here, I'm just going to say, let's assume, let me say I got another method here. Let's say get older. And then I would say integer and maybe some I. And then here I can say age plus equal I, right? Let's say that's a mutator method in the person class, okay? I'm just thinking on my feet. So here I can say P dot get older. And then I want get older by, let's say, 3 years, let's say. Okay, let's see exactly call by value is going to work. So we got two different classes here. Two different. Okay, one here and one here. All right, so far so good. So in order to use this utility, let's create an object from there. So we can say util, u will be new util. And then I'm just going to say u dot change age. And then P. All right, and then you can maybe write some JUnit test to say, now if I say assert equals, and then here I want to say Jim.age. What should that be? Well, it used to be 23. Presumably it should be 26. But let's see exactly how that's going to happen. Presumably this one should pass. But let's see how. Okay, what's going to happen is, when we actually try to, you can think about, we create this object here, u, and then we're going to say change age. So we are calling this method over here. Okay, and then, oh, sorry, there's something I just got it wrong. Sorry, I don't have a compiler, but no excuse. This one should be Jim. All right, that's what I really meant to say. Okay, so the way to fix, to really trace it would be, call by value tells you that this is so-called arguments. And we are calling this method here, and the P here is so-called the parameter. And if we try to make a method call, like over here, so call by value tells you that there will be some implicit variable assignment that's going to happen. All right, I'm going to write it down. Call by value tells you that the parameter P is simply going to be a copy of the Jim. This is implicit. You don't really do this variable assignment yourself, but it's going to be done behind the scene. That's exactly what call by value really means. All right. So the consequence of doing this is P is now going to point to just the same object as Jim is. Agree? Right? That's variable assignment. So now when you say P dot get older 3 over here, you're basically saying I'm going to just modify this particular object. So it's going to be modified to 26. So that's why when after we have executed this method here, when we check the age for Jim, it's still going to be 26 because Jim and P, they point to the same objects. All right, that's call by value. That's just a very typical use. So array will be the same because array is also an object. Right? Okay, good. Yeah, I'll get to you. So guys, that's a very like a 3 minutes crash course on a call by value. That's basically the essence about how you can use call by value. If you want to see more, background study, right? It's there. Question?
So if we were to create a new person object using and we were to put gym.age, would it also point to the gym age?
Mm-hmm.
Or is that just
so where do okay? So let's be very precise. So where do you want to create a new object? You mean inside here?
So no, let's say that we do person and then we use gym.age as the parameter.
Oh yeah, sure.
Is that going to be pointing to gym's age?
Yes, exactly. Yes, exactly. So for example, so that'll be another. Okay, I'll write it down here. For example, Jim, and then let's say John, and it will be equals person. And here, rather than passing an integer, I might say Jim dot age. That's what you're saying, right? Yeah. Good. This one here, actually nothing to do with well, you can think about Jim dot age over here. Well, call by value in some way, yes, because Jim dot age is just an integer 26. So for the primitive type, it's much easier. You can think about we're just making a copy of 26 itself, right? So what that will do is it's simply just going to create John over here, and it's just going to point to a different person object because we got the new keyword again. The new keyword over here. And that one there, the age will just be a copy of 26, which is 26 over here. Different persons. And it's a copy of 26. So just separate copies of 26. Yeah. Yep. All right, so just make sure you kind of understand the call by value, especially when you're passing some argument that's reference type. That's really important. So when we do the example together, that's something you also want to watch out for. All right. All right, guys, any other questions? Good. Yeah, call by value, very important. All right, so we went through this pattern here, which we're going to emphasize again. But for those of you who want to see some basic example on recursion on the array, you can look at the all positive and it's sorted. That's also in the background study, right? So these are also very straightforward, but it can really emphasize the point about this pattern here. All right, so what we should do now is to look at the more advanced example. But why don't we take a short break by taking some trial attendance. All right, I'll stop, pause the recording now. Alrighty, okay. All right, so let's now take a look at this problem here, and you can also download it. I'm pretty sure I cannot finish everything about this problem today, which is okay. At least I want to give you guys some insight about how you can sketch the solution. And if I can also maybe give you a little bit of Java code to get started with, I can also do that. But I think the very important part is about tracing. I may have to leave that until the beginning of Tuesday. Wouldn't take that long, but I don't think I can do it properly today, but we'll see. Okay, you can click on the link, or you can simply go to the lecture site, and there you will see that under exercises over here, the starter project, and here. Okay, so let me show you from scratch. You can download this starter project here. I assume you know how to do it. And let's say it's a zip file on the desktop. So this is something you will also need to do for your programming test. You will be given a link to download some starter project for your programming test, 1 and 2. So let's say it's on my desktop. So what I need to do is I'm going to launch my Eclipse. Okay. And by the way, Eclipse, you can download it to your machine, or you can go to remote lab, either way. I'll include some instruction for you in the programming test assignment number 1 as well. All right, usually first time will be a little bit slow. Bear with me. So once you launch your Eclipse, I can, so for now, I assume that I have a folder on my folder over here called workspace, under which I got 2101. Okay, that's the assumption. You can do whatever structure you like in your case. All right, I already set up the workspace properly. Okay, and then I'm going to say launch. In the beginning, the workspace will just be empty. And the critical step is to import the project into Eclipse. All right. There we go. Okay, good. Yeah, the font size could be a little bit smaller for the icons, but when you see the recording, you will see it's definitely readable. Well, I'll read out anything to you. You can just simply, you can see the workspace. You don't have the project just yet. You can go for File and then Import. And then you will see under a tab called General. Under General, Existing Project into Workspace. So this is exactly the step you have to follow for programming test. Okay, and then there is two options over here. One of them, the second one, you gotta click on the radio button. It says Select Archive File, which means to select a zip. So I'm gonna browse, and then I'm just going to my desktop, for example, and choose that zip file I downloaded from the lecture site, right? And then say Open, and it will just show something here, okay? Which means it's going to be imported, and I'll say Finish. Okay, that's it. Okay, and then that's a project. Okay, so when you click expand the project, there are two packages. One is called JUnits tests. That's something that's going to specify some starter usages, as I explained last time. So that's something for you to start with. So if you go to click on that, that one shows you about 13 or 13-ish different test cases, right? So I assume you guys have already seen how JUnit tests should be understood. Take a look. If you got trouble understanding exactly what's going on, drop by, right? I will go over with you. But we're going to focus more on the other package called Model. Under Model, there's a method class called Recursive Methods, for example. In that class there, we have the method we're going to do, split array, which has an input array. All right, that's the one to start with. And there's already some comments over here just to show to you some hints about how to program the method. All right. Okay, so far so good. And one thing you can try right away. Okay, so for example, I can click on the JUnit test class over there, right click, and then I can say run as JUnit test. But hilariously, about half of the test cases are already passing. It's simply because it's returning Boolean. So we somehow give half of the test cases in which we're expecting true, the other half expecting false. That's why if you just return true or false always, you always pass half. But don't worry, you are not that lucky in the programming test. We'll make sure we set it up differently, right? You shouldn't get passing mark that easily, all right? Anyway, so just don't be too satisfied by passing so many already. You gotta fix it so that you pass all of them. All right, so remember I mentioned about regression testing in the syllabus, right? Regression testing simply means we got this set of unique test cases given to you. You're just going to rerun them over and over whenever you're trying to make a draft version of your solution. Hopefully, eventually, maybe in the 10th trial, you will be able to pass all of them. Okay, something like that. I'm going to leave the Eclipse for now, but at least you know how to get started. I think today, to be realistic, I got about 12 minutes. I will definitely talk about exactly how to get some intuition about a solution. I'll spend time on that. And then I might give you a little bit of hints on the programming side about how to declare the recursive helper method. I'll do that. And then maybe that'll be some nice exercise for you to try it out over the weekend, right? If you can get succeeded, awesome. If no, come back on Tuesday and then we'll go over again together. All right, let's now take a look at the problem here. And guys, as I said, it's a more advanced one, right? How about for the benefits of those of you who haven't really seen the problem, why don't you take 1 minute to read it, okay? I'll give you guys some time, okay? 1 minute. At least you want to know what the problem is. Okay, another 30 seconds. And of course, you can also feel free to take a look at the example usages over here, which I turned them into JUnit tests already, right? Okay, let's now, assuming that you have read this already, let me not repeat, Okay, but I'm going to explain a little bit about the example over here, and then we'll talk about some intuition. So this one here, you can see the array has two elements, 2 and 2. The reason that it returns true, because somehow we can divide these two elements into two groups. Oh, so here we're assuming there are always two groups, group number 1 and group number 2. And the way to split them such that the sum of group 1 and the sum of group 2 will be the equal is maybe put this one into group 1 and put this one into group 2. Easy. So that's why it's true. How about this one here? There's no way. Because if you put 2 into group 1 and put 3 into group 2, what will be the sum? 2 versus 3. They are not equal. What if I put 2 of them into a single group? Also not possible, because you get 5 versus 0 for the sum. Also, they are not equal. So there's no way for you to split these two numbers into two groups. So that's why it's going to be false. The idea would be you somehow want your recursive method to exhaustively consider all the possible combinations of putting the elements in the array, which can be arbitrarily large, right? Can be 10 elements, can be 15 elements, etc. You want to exhaust, your method wants to exhaust all the possibilities if there, for among all the possible ways to put the element into two different groups, simply don't give you the equal sum, you'll return false. If there's at least one way for you to do the equal sum, you should return true, right? That's kind of insight you want to get right away. And this one here, also quite obvious. Well, for us to see that, we can get some very quick intuition. I can put this one into group number 1 and put these two into group number 2, right? So there's a way. So that's why it returned true. Question?
If we were to do split array, go with 5, 3, and 2, that's a fail or a pass?
Okay, good question. So let me write it down. It's definitely a very good test case. Let's now talk about it. If I heard you correctly, you said 5, 3, and 2.
Yeah.
Definitely, it will be true. Because I can put this one into group number 1 and put these two into group number 2. I'll give you one more. If you don't mind, let me modify your example here. I can even say 2, 5, and 3. This will also give you true, because you don't necessarily have to put two consecutive elements into the same group. No, not really. I can put maybe 5 into group number 1 and the remaining 2 into group number 2. That's also one possibility. So also it should be true. All right? Good. All right, so now I got about 7 minutes. Let me see. I'll only give you some intuition. All right, so you guys can give a try over the weekend on Eclipse. Intuition. And you guys took 2030, not EECS, Math 2030. You learned about how to figure out combinations, right? All right, let me remind you about this problem here. How many ways to put n elements into m groups? Guys, a test for your 2030 knowledge. I didn't teach you that, so you gotta help me. I heard factorial. No.
The choose function?
Choose on the right direction. Also no.
2 to the n.
2 to the, also not, getting closer. 2 to the power, no, not 2, not 2. Because m and n here, right? Of course, for our particular problem here, we're assuming that m is equal to 2, but not in general. All right? Okay, so the answer should be n to the power of n. Imagine that. If I got, let's say I got n elements. Oh, beg your pardon, n elements. That's what I meant to say. Okay, n element. N can be arbitrarily large. Can be 1, can be 2, can be 100. I got n elements. And now for each one of them, I'm going to consider them separately, independently. For element number 1, how many possibilities do I have? N. I can put it in group number 1, I can put it in group number 2, all the way to I can put it in group number n. I got n possibility. Also, independently, for element 2, I also got n possibility, right? So overall, it's going to be n times all the way to n times. That's why m to the power of n. All right, 2030. All right. If you are feeling frustrated about it, we can also talk. Even though I got that's the limited thing I know about 2030. All right. All right. So that's important intuition because amazingly, you only have to write in your recursive solution less than 10 lines of code to solve this. However, when we trace that recursive call at the runtime, it's actually going to do this exactly. That's the amazing part. All right. And now I'm just going to give you guys some very quick run through about what's going to happen. Okay, I'm going to do 4 minutes. Okay, good. I will get to the insight in a bit. Okay, so now. So let's say this. If I have over here 2 groups, can we just assume that this is group number 1 and this is group number 2? All right, group number 1, group number 2. Let's now take this example, this one here as an example, this one here. So we got input, only got 2 elements. According to our formula, how many possibilities are there? 2 to the power of 2, 4. All right? We start with this, where each group is simply just empty. And then you can imagine that somehow we have to make 2 different recursive calls, somehow. For the first recursive call, we are making the assumption that we're going to put the first element 2 into group number 1. And on the other recursive call, we're going to put 2 into the different group. And these 2 branches are completely independently. We're going to consider them separately. That's how we explore exhaustively. All right? So now, what will be the updated thing? So here, if I put 2 into group number 1, so 2 will be here. So group number 2 remains to be empty. If I put 2 into group number 2, so group number 1 remains empty, and group number 2 will be here. Are we okay with this? All right, you can see that, right? And these 2 are completely independent. And we still have our second element to look at. So that means we're going to make further recursive call. And for this one here, that means this 3 here may be put in group number 1. And 3 here may be put in group number 2. And group number 1, and also group number 2. All right? Let me now write them down very quickly, right? So that means, guys, what should group number 1 be now? 2 and 3, right? Because 2 is already there. 2 and 3. Empty. And then, so these will be 2 and 3. All right? And for this one here, it will be 3 and 2. And this one here will be 2 and 3. You guys can double check. I'm just doing that quickly. And you can see out of all the 4 possibility over here, do we have at least one valid one with equal sum? Yeah, for sure. For example, this one here is pretty good. So that means you should return. I beg your pardon, sorry. What I really meant to say was, out of all the possible ways to group, you can see it's unequal. 5 versus 0, 2 versus 3, 3 versus 2, 0 versus 5. None of them is possible. So you should return false. All right? All right. So I want you guys to really understand about exactly this kind of tree structure over here. When we trace the recursive call on Tuesday, that's exactly what's going to happen. Right? I want to do one more thing so you guys can really try to see how you can make this happen. Hint number 1. You want to define your recursive call in the recursive helper method in such a way that it's going to make 2 separate recursive calls. Each one of them is going to consider the current elements being looked at either to group number 1 or to group number 2. That's really the key. All right? I want to do one more thing, and then give me 1 minute, okay, and then I will let you go. I'm going to just type one line for you over here. What you really need to do is you will need So this method here is pretty good, but we just need a recursive helper method. Okay, over here. So I'm going to, so this will be a recursive helper method you will need. And that one there usually should be private. And then it also returns a Boolean. And call by value. So I'm going to call that split array. That's the original method. I'm going to call it helper. Just a standard way of naming the method. And then I'm still going to get my integer array numbers, call by value. And integer I here is like a from and to that we spoke about before the break, right? About specifying the ranges. But we just need a single one. And then this is the thing. I'm going to get integer here. This will be the sum of group 1. Integer sum of group 2. All right, and then I'll just say return false for now. So this will be the recursive method you will have to define. All right, and how do you interpret these two? The way to interpret these two, I'll show to you. Okay, and then I'll let you go. Let's go back to here. All right, think about initially, the sum of group 1 will just be 0 and 0. And then one possibility will be we may have to add the element 2 into the sum of group 1. So that becomes 2 versus 0. And another recursive call, we are going to put the 2 into group 2. So the sum will be 0 versus 2. So we don't really have to numerate the elements in the group. We just have to accumulate their sum. All right, so that's kind of the hints for you. Give a try over the weekend based on the method header for the recursive helper method. If you cannot really get it done, that's okay. Look at the basics. All right, see you next week. Thank you.